7 kilometers under the sea, inside a crushing wall of mud and basalt, India is building its future. But with an 83% cost overrun. Is this $15 billion project a masterstroke, or a mistake? Welcome to the MAHSR project. As of January 2026, over 332 kilometers of viaduct are finished. But the hardest part is just beginning. Today we analyze the secret engineering of the E10 Shinkansen, the Tetris machines lifting 970 tons, and the truth behind the 2027 deadline. At 320 kilometers per hour, even a 1 millimeter error in the track can lead to catastrophe. This is the Mumbai-Ahmedabad High-Speed Rail, a project that isn't just being built, it's being manufactured. Today we go beyond the headlines to analyze the extreme technology making this possible. To build 508 kilometers fast, you can't build on site. You need a factory. This is the full span launching method, or FSLM. Each girder is 40 meters long and weighs exactly 970 metric tons. That is the weight of 7 Boeing 747s. The girders are moved by a specialized transporter with 88 independent wheels, ensuring the weight is distributed so perfectly it doesn't crush the bridge it's driving on. As of this month, the MAHSR has achieved a world record, casting and launching over 320 kilometers of these spans with a precision tolerance of just 5 millimeters. L&T's indigenously built transporters move these giants at just 5 kilometers per hour. As of this month, 415 kilometers of piers are standing. That's 81% of the total pillars required. Package C2 is where engineering dreams go to die. We are digging a 21 kilometers tunnel with 7 kilometers sitting directly under the Thane Creek. This isn't just a tunnel, it's a pressure cooker. Engineers are using a mix of NATM, new Austrian tunneling method, and massive TBMs. We just achieved a 4.8 kilometers breakthrough in the Gansley section. The challenge? Preventing seawater seepage under 65 meters of pressure. This is India's first undersea rail tunnel. 7 kilometers of it sit directly under the Arabian Sea. We are using a slurry pressure balanced TBM with a diameter of 13.1 meters. Why slurry? Because the soil here is a chaotic mix of basalt and soft marine clay. The TBM injects a pressurized liquid, slurry, at the front to balance the weight of the ocean above. If the pressure drops even slightly, the sea floor could collapse. If it's too high, it blows out the seabed. It is a 24-hour-day mathematical balancing act. India isn't just buying trains from Japan. We are Indianizing them. The Shinkansen E10 is a modified beast. It features upgraded cooling systems to handle 50 degrees Celsius heat and specialized dust proofing for the Ahmedabad plains. Notice anything missing? There are no stones. High-speed rail uses ballastless track, specifically the Japanese J-Slab technology. 320 kilometers per hour, stones would fly like bullets. Instead, the rails sit on precast cement asphalt slabs that absorb vibration and prevent heat expansion. India is using the Japanese J-Slab system. These are precast reinforced concrete slabs, 2.4 meters wide and 300 millimeters thick. The train is controlled by DSATC, Digital Communication-Based Automatic Train Control. There are no roadside signals. The brain of the system calculates the exact position of every train on the line. If a train ahead slows down by even 5 kilometers per hour, the train behind it automatically adjusts its speed via wireless signals. It is an invisible safety net. While trials will start with the E5 series in late 2026, the future belongs to the E10 Shinkansen. Derived from the experimental ALFAX, it features L-shaped guides to prevent derailment during earthquakes and a 22-meter-long nose to eliminate the sonic boom when entering tunnels. It's not just a train, it's a safeguard for the next 50 years of Indian transit. While the viaducts dominate the skyline of Gujarat, the most expensive single structure of the project is buried in Mumbai. The BKC station is a 1.5-kilometer-long underground monolith. It is 36 meters deep, the equivalent of a 12-story building sitting on its side. Engineers had to excavate over 2 million cubic meters of earth while protecting the nearby Mithi River. This station isn't just a stop. It is a waterproof concrete bunker designed to handle the weight of Mumbai's financial district above it while staying dry during the heaviest monsoons. At 320 kilometers per hour, human reaction time is too slow. This is why the MAHSR has no physical signals alongside the track. Instead, it uses DSATC, digital communication-based automatic train control. The brain of the railway knows the exact position of every train to within a few centimeters. If a train ahead hits a bird or a minor technical glitch, every train behind it for 50 kilometers automatically adjusts its speed. This is backed by a 24-hour centralized power grid with 3 redundant backups, ensuring the bullet never loses its breath. The operating speed is 320 kilometers per hour, but the design can handle 350 kilometers per hour. This will cut a 7-hour journey down to just 1 hour and 58 minutes. As we stand in late January 2026, the Surat-Bulimara trial section is 18 months away. Physical progress is at 55.63%. Financial expenditure has crossed 85,801 Indian rupees crore. The real question isn't when it will finish, but how it will change India. Just as the Tokaido Shinkansen integrated. As we look at the progress in early 2026, the first trials in August 2027 are looking realistic. Build theory will be there. Subscribe to see the world's most difficult engineering conquered.